Look at this data moving through a network. When it stutters, it represents the physical bottleneck hidden inside almost every modern AI workflow, cloud dependency. This diagram maps the standard API pipeline. A local trigger packages data, sending it across a network for cloud processing. Bouncing across external nodes introduces unpredictable latency, compounding into hard bottlenecks for automated operations. Beyond speed is privacy. When proprietary data crosses third-party boundaries, you lose control, exposing sensitive payloads to breaches. The solution is structural. We cut the cloud connection entirely, drawing a hard, isolating perimeter directly around the local machine. To achieve high-tech, a private sovereign intelligence layer to replace external cloud reliance. This requires constructing an operating environment that is completely localized and air-gapped from the wider internet. Within this closed system, we deploy autonomous cognitive agents that execute logic and process data exclusively on personal silicon. For previous generations of computing, local machines functioned largely as thin clients, terminals used primarily to access remote compute. Today, the local machine operates as the primary inference engine. Stripping away third-party routing upgrades a vulnerable, latency-prone workstation into a hardened, automated cognitive engine. This schematic outlines a unified CPU and GPU architecture, operating within a rigidly bounded pool of fixed memory. Attempting to run an uncompressed open-weight model natively hits a physical wall. The raw parameter size fails to load, exceeding the available unified memory limits. Raw processing compute is rarely the actual issue. The primary bottleneck for local inference speed is memory bandwidth, the strict physical rate at which massive model weights are read from memory and fed into the processor. To bypass this physical bottleneck, engineers apply a mathematical compression technique known as model quantization. The process mathematically truncates the model's precise 16-bit floating point numbers down to compact 4-bit integers. This drastically reduces the file footprint. The compressed volume now smoothly slides within the fixed memory pool, allowing the hardware to load it entirely. Compressing the data does result in a fractional loss of mathematical accuracy. However, testing demonstrates that dropping to 4-bit precision preserves the overwhelming majority of the model's cognitive utility, while reducing its physical size by nearly 75%. This mathematical compromise between precision and size is what enables the sovereign intelligence layer to execute on consumer hardware. By shrinking the parameters, we eliminate the physical requirement to rent clusters of enterprise-grade server racks for daily, repetitive, automated workflows. In system architecture, resolving physical hardware constraints must precede designing the software applications that run on top of them. AI research labs consistently release highly capable open-weight models, providing engineers with direct access to raw neural networks that are immediately ready for this quantization process. Quantization is the specific mechanism that allows enterprise-grade cognitive logic to fit within the physical constraints of local silicon. With the model successfully loaded into local memory, the focus shifts from the internal hardware layout to the external security boundaries of the machine. Operating a local LLM securely requires constructing what is strictly defined as an air-gapped sovereign environment. This diagram illustrates the necessary operating system configuration. We enforce isolation by explicitly blocking all inbound and outbound network port communication tied to the inference engine. Severing these external network dependencies ensures absolute zero data leakage. Regardless of the prompt payload fed into the model, the data has no physical route to leave the machine. There is a secondary performance benefit to this isolation. The speed of execution is completely decoupled from internet traffic fluctuations and external API load balancing. The inference speed is now strictly dictated by the host machine's local unified memory bandwidth, operating independently of the outside world. Instead of mitigating the highly variable latency inherent in cloud-based architectures, the system achieves a consistent deterministic execution time for every run. The air-gapped perimeter replaces the need to trust a cloud provider's policy with the physical impossibility of external access. Once the hardware is optimized and the perimeter is secured, we transition up to the application layer to interface with the model. Observe this split screen. On the left is the standard web chat interface, and on the right is a blank automated terminal. typing manual prompts into a chat box introduces a human bottleneck, limiting the execution of high-volume cognitive tasks. The architectural alternative is deploying autonomous agents to run entirely as background processes. These agents function as system daemons. They sit silently in the background, continuously monitoring designated directories on your hard drive. This flowchart outlines the trigger mechanism. The agent intercepts low-level operating system events. The moment an event fires, it automatically extracts the raw payload data, pipes it directly into the localized quantized model, and utilizes the output to execute a predefined script, completing the cycle. In a theoretical engineering scenario, an agent can be scripted to watch a meetings folder. The precise moment a text file of rough notes is saved, the agent intercepts it, summarizes the text locally, and generates a formatted document. During this entire cognitive processing phase, zero human interaction with a user interface is required. Hooking directly into an operating system event provides an instantaneous trigger. It bypasses the physical delay of a user opening a browser, copying text, and typing a manual prompt. Because this entire sequence operates within the air-gapped perimeter, the raw files and generated summaries never leave your device. Intercepting file system events transforms a local LLM from a passive answering machine into an active, autonomous background coworker. Looking at the constructed system stack from a macro perspective, we see how the hardware, security, and application layers integrate. At the foundation of this completed architecture, quantized models execute within the memory limits of personal silicon. Surrounding this core is an air-gapped security shield, guaranteeing data sovereignty and eliminating latency. At the top layer, autonomous agents intercept file events to drive continuous cognitive labor. Only by combining all three of these structural elements do engineers achieve a true private sovereign intelligence layer. Maintaining a dependency on external APIs leaves proprietary enterprise workflows exposed to hard latency bottlenecks and third-party data harvesting. Local hardware has officially evolved from client-side terminal status into secure, sovereign infrastructure. Mastering this multi-layered architecture is the definitive step toward achieving high-speed workflow automation with uncompromising total data privacy.